So, that's okay. So this is being recorded. So we were talking earlier about how this has been about 2.5 years in the making. So it's great, Tim, to finally have you here. And please join me in welcoming Tim to the podium.
Okay. See if I can find my cursor on the right screen here. Yeah, there. Got it. Okay. It is a pleasure to be here, and thank you, Al, for being such a gracious host and inviting me to give this lecture. I thought it was also fitting that I won't show you crazy aromatic structures, but I have a real fascination with aromatic molecules, like Professor Dauben had, and we do a lot of kind of crazy syntheses of anti-aromatic and as well as non-benzenoid aromatic molecules, and in fact, a lot of that is very important to some of our work in magneto-optical materials, which we're very actively working on. So it's an honor to give a lecture for Professor Dauben. Okay, so today I'm going to talk about what's a relatively new area in my group, and it has to do with emulsions. And you think about emulsions, you think about milk or food, but these are complex emulsions. And this is the first thing is a quiz question, but for graduate students, no faculty, unless that will be at the end of the lecture. And I want you to figure out how we made this picture here. I like it because it looks like flying saucers, like we're on, the sci-fi kind of things that when I was a child. This is about the level of special effects back then. But they're all, you might notice they're all in one direction, and they appear to be half hemispheres. Okay, so why are we playing around with emulsions? Let me just, I think I got to switch slides. Okay, well, as Al mentioned, I have a fascination with sensing. In fact, the enduring thing in our research group is to create sensors of all types: mechanical, chemical, biological, optical, strain sensors. We've done them all, and radiation sensors. We just love making sensors, and I try to see sensors in things. And I've always thought about biosensing as often practiced as you're immobilizing things on solid supports. Yet, when you think about the molecular recognition or the biomolecular recognition of a cell, it's very dynamic. You have these bilayers, which are technically liquid crystals. They're liquid crystalline in nature. And the molecules here that are basically anchored, floating around like little icebergs, it might be glycosylated, phosphorylated, different things are going on, but they are able to dynamically move around. They're able to cluster. That's what focal adhesions are between cells. And so that dynamic part is something that's really missing in a lot of biosensing. And I thought, gee, if we can emulate that, maybe we can make, new generations of biosensors that have better fidelity, have different modes of action. And so we began this pathway many years ago, actually looking at things, air-water interfaces, and did a lot of background of it. We were never really able to get things that really appealed to me from a sensing standpoint. We did a few things over time, but they weren't really not, moving the needle as much as I would like. And we thought we needed something else. And so I was always, fascinated by this field of making complex emulsions. Okay, these are emulsions that have two fluids dispersed in water. So in this case, what I'm showing here is the red component is an organic phase. The continuous phase is water, and the gray point around it is a fluorocarbon phase. And fluorocarbon and hydrocarbons tend to phase separate, as you know. And so what I'm going to show you is that this extra little modality to these droplets tends to give us new properties that we can use to make chemical sensing work. Okay, so I'm going to exclusively go with the organic fluorous one today, but we've made others. We've made ones that have 3 different phases, but that's something I couldn't really fit in today's talk. Now, a nice way that we make these that's really nice, that's scalable, has used something called the lower critical solution temperature, or upper, excuse me, lowers with polymers. Getting my uppers and lowers down here. So what we have here is what I'm showing you here is a dynamic phase separation of a heated mixture of a fluorocarbon, hydrocarbon, where you heat them up and entropy takes over, they mix. And if you cool them down, they phase separate. So what we can do here is we can make very crude, polydisperse emulsions like this by just heating things up towards one phase. We put it in a bunch of water here. Water's our continuous phase. And you can just shake them. You can go in the lab yourself and do this. You can shake them, and you're going to make an emulsion phase that looks like this, provided you have a surfactant in there. We'll talk about surfactants in a minute. But this is kind of nice because we can make these on different ways and simplified routes. And we can make them, monodisperse using microfluidics. This is a device where you could ordinarily put two different fluids in there. In practice, we're just putting one because we're heating it and we're adding it in a water phase. But you can make these, very monodispersed. And you might notice also when you get these spheres so nice and monodispersed, they tend to pack in two-dimensional hexagonal networks. If you can just put a few in a petri dish, put them, let them kind of flow down the end, and you'll get these nice hexagonal patterns. Okay. So now let's talk about surfactants. So we have fluorocarbons and hydrocarbons. Our favorite surfactant in the fluorocarbon area is something called zonal. And zonal is essentially a oligoethylene glycol that likes water with a fluorocarbon tail on it. And so if you have only zonal into these mixtures, when we spit these little droplets out, the fluorocarbon ends up on the outside because that is stabilizing the interface with water. So this is a droplet that has a shell of fluorocarbon encompassing the hydrocarbon, which we throw the red dye in so we know which one's which. Okay. Now, alternatively, we can use sodium dodecyl sulfate, which clearly is an organic surfactant, and that reverses things. So the organic phase is on the outside here, and the fluorocarbons on the inside. Okay, so this would be a, hydrocarbon within a fluorocarbon within water. This is a fluorocarbon within a hydrocarbon within water. Okay, so we'll keep track of these. Now, these things, what you might also notice is they're perfectly round. And the reason they're perfectly round is that is the minimum surface area between the outside world and the droplet. So you want to minimize surface tensions. One of the beautiful things about these droplets, they're liquids and they come to equilibrium very fast. Any of you that work with polymers know that polymers do not come to equilibrium fast. They are intrinsically non-equilibrium systems. So this is really nice because things go where you tell them to go. You just tweak it a little bit, it changes, it settles in, and it hits the same point every time. It isn't like there's a path length dependence to it. Okay, so we have these different phases. I showed you about how we can make, a case where the hydrocarbons on the outside and the fluorocarbons on the outside. Now you might notice that the way I've drawn these, I'm not putting the other droplet right in the middle. And that's because I want to emphasize that if we're going to put these on a surface, there's gravity. So imagine that this is the surface they're resting on. Gravity is going up and down here. Fluorocarbons are denser than hydrocarbons. So they end up sinking to the bottom here. The hydrocarbon, like a balloon, goes up. Similarly here, if we work in the middle, what we call a Janus droplet, where we tend to balance the different interfacial tensions, we can get this other phase. Now, in general, we'll get a minimization of this phase here in the middle, but of its surface area, it's really dominated, however, by these outer interfacial tensions, the structure, because those interfacial tensions are far bigger than the fluorocarbon hydrocarbon. The fact that we can just heat these up around 35 degrees or something and they mix should let you know they don't hate each other that much. They don't hate each other like they hate water, right? So these interfacial tensions are really small. They're very small, only 1 millinewton per meter, where water is, with a hydrocarbon is like 70. So they're 70 times lower. Okay, so that's kind of some basics of the emulsions we're working with. Now, one of the things we found, we can make these individual droplets, but one of the things my postdoctorate at the time found, Lauren Zarzar, was that she could actually turn these things inside out without them coalescing. So usually what happens, I mean, if you whip up cream, essentially whipping cream, you make, the fluid part, you whip it into a continuous phase. That is coalescence of those particles. And so that can happen with mechanical motion, or sometimes if you're just playing around with, pHs and different things, that'll happen. So we were surprised, and actually maybe not in hindsight, but it wasn't known that you could basically take these kind of complex emulsions. You could start out with the hydrocarbon on the outside and add a whole bunch of this zonal here on one side, and you could basically flip them inside out. And there's a continuum, there's a gradient of our zonal across here. Now, remember here, I'm looking top down in this case. That's why we have drawn it in the middle. The microscope image, even though the fluorocarbon sag into the bottom, it's going to look like this from a top-down view here in the microscope. Here, you're not seeing that because you're looking straight down on a Janus droplet. Right here in the middle, there's going to be something called the perfect Janus, where they're exactly matched, where you have this high symmetry, okay? But it's really there. You're just not seeing it because you're looking from the top straight through it. This is just a side view so you can see it. So it's really quite amusing to watch these types of processes in real time. So what Lauren did is she just had an array of these, and she threw in some zonal. There's some, convection here of the solvent. You can see they start switching. Okay, you see that they're starting to switch. They're going to a Janus here. Look at how they basically start moving. They even have inertia. So these things are fluids. They're really flexible. They tend to orient really quickly. Gravity's taking over. They're wiggling a little bit, but eventually they're coming where the fluorocarbon's on the outside here, and we've done that. Now, you can switch them other ways. Here's a way where we can use a surfactant molecule. It was known in the literature. We just remade it. When this surfactant molecule is in its linear form, it's a good surfactant. Nice rod-like thing with a charge group on one end, hydrocarbon on the other. That's what you want in the surfactant. When you bend it by doing a photoisomerization, it's a less good surfactant. So what we did here is we can start out with the fluorocarbon in the middle, hydrocarbon on the outside, but when we isomerize it, the hydrocarbon isn't as good of a surfactant, and the zonal takes over, and it switches to a Janus. And you can see these two up here at the top got stuck on their side. There was something at the surface there that's anchoring them and keeping them on the side. And they're smaller ones. The heavier they are, the harder it is to anchor them because you got more weight. You got a bigger gravitational force changing it. But you can see how you can switch these.
You don't see the side of the Janus because of the density?
Yes, it's spontaneously aligning with gravity.
Okay, that's pretty cool.
Yeah, no, it was actually when we were starting thinking about sensing patents. This is kind of a funny story. I was so interested in this gravity. I said, "Oh, we're using this gravity alignment. That's going to be one of our claims." And the patent attorney says, "Tim, you can't patent gravity." But I want to patent gravity. Okay, but it's gravity alignment. Okay, so other cool thing. Okay, these liquids, hydrocarbons, fluorocarbons, they're transparent, but they have different refractive indices. So when I look at two of them, when they're phase separated, I got a whole bunch of them here. They sank to the bottom here of this flask. There's a bunch of water in here. They look like milk. They're scattering light because the different refractive indices, you're bending the light every which way, it's scattering light. Now, if I have the right fluorocarbon, hydrocarbon, such that and the right ratio, so that if I heat these up and they're a single phase, and I make it exactly equal to the refractive index of water, you don't see them. So this is the same solution. Took a heat gun on it, boom, they go away, let it cool back, they come down. Okay, so they are refractory optical systems. And not only are they just refractory in terms of scattering like milk, they are lenses, okay? So that was another thing that was really important to us. Because I mean, I think you all are familiar with droplets or lenses. That's why we see rainbows. That's why you put a drop of water on a newsprint, you can see it magnifies it. And so these are lenses that can be dynamic. And these are actual photos of the side-on photos. We use a microscope. We have a side-on microscope to take pictures of these. These are ray diagrams that were measured by my colleague Matthias Kolla in mechanical engineering. And I think what you can see is you have some droplet morphologies, they have nice focusing conditions here. Over here, they're dispersing the light. And here in the middle, the perfect Janus, actually collimated light comes in and collimated light comes out. It transmits images, as I'll show you in a minute. But I think it's really kind of, to me, it's kind of profound. When I look at these three right here, I could do some flashcards, and I don't think many of you would get right which one is 1, 2, and 3. There are very subtle differences here, but look at the changes in the focal length on these. Okay, so our motivation was creating sensors. So what kinds of sensors were we interested in? Well, we've been very interested in food pathogens because, you know, there's lots of ways to do it, but they're just not fast enough, or they're too complicated. And in fact, you're constantly seeing recalls of food because people had to ship it. They were losing shelf life. They had to get it out there. And they just didn't have enough time to properly test it. So you need things that can detect down to 1 colony forming unit in, you know, less than 12 hours. Okay. Just a single salmonella, single listeria is what you need to detect. Okay, so we've been working on this and using these kind of refractory optic effects to do this. And so again, here's the different refractive indices of water and our organic and our fluorocarbon phase. Notice the fluorocarbon phases are lower because it, you know, you got those electrons really localized by that strong, you know, the strong electronegativity of the fluorine. Okay, so remember I told you we can get the focusing condition, we can have the ones that basically collimate light, we can get ones that disperse light, and we can also use the perfect Janus here that would ordinarily collimate it, but if we tip them on their side, they're going to scatter light. So we can make use of all these effects now to start detecting different types of bacteria. Now we've decided to start with something which is probably not the best molecular recognition, but it was something that, you know, we knew we could work with, and that was to use the carbohydrates that are expressed on the surface of these different bacteria. Okay, and they're not perfectly unique. There's lots of things like mannose and like, but it was a good place to start. And so what we did here is we made surfactants. We just made a simple carbohydrate surfactant. Just took a mannose and substitute a long alkyl chain on it and put it on our droplets, and we made droplets that had that surfactant. In this case, we're just using something that is a model for a lectin, or for the binding of these carbohydrates to bacteria, something called concanavalin. It's a tetrameric protein that tends to bind mannose. And what you see here is ordinarily, without any of this concanavalin around, we can take these droplets. It's kind of fun. You can just tap them on the side, they'll tip over, but they kind of right themselves, and then they come back. Gravity aligns them. So they just spontaneously align this way. But if you throw in some concanavalin and you tap them, they get stuck together. They agglutinate. And they stay in that row, that configuration. Now we can quantify that. We wrote Suchil Savagantra, who is now a chemical engineer at University of Arizona. Now he's an assistant professor. Suchil wrote some nice programs where we could basically quantify this by doing just automatic image processing and analysis to get out how many of these things. You have to first figure out, you know, all the what are the objects you're looking at, and then look at how they overlap. But he was able to do this with some computational methods, and you know, you can get nice quantitative data for measuring, in this case, is concanavalin, simple concanavalin. Now we took this on further in collaboration with Peter Seeberger, a colleague of mine who focuses on carbohydrate chemistry. And we went and showed that we could do this now for E. coli. And you can work with a couple of types of E. coli, ones that are mutated. They don't bind mannose, some that do as our control. But again, with E. coli, without the E. coli, you can tap them, they stay put. With E. coli, they'll tend to agglutinate. We actually found you can do the Suchil method, where we can basically use a magnifying glass, essentially a smartphone, to capture images, process them, or you can do something really simple. We just take a QR code. Ordinarily, when it's like this, remember the Janus ones transmit parallel, parallel light comes in and comes out. It does not diffract. We put these over the top. You can see the QR code. You can read it with your smartphone. You agglutinate them. You basically block it. These are highly scattering objects. And so now you can have something that you can just basically just use a QR code to get a 10 to the 4 bacteria detection, which is actually pretty good. That's kind of close to what, you know, current state of the art in terms of raw detection methods are. Okay, so as I mentioned, carbohydrates was a good place to start. It was easy for us to make a surfactant out of carbohydrates, but we really need to move on to antibodies and other types of recognition that are more robust and more specific for, you do not want false positives. You don't want to say that every, sample coming out of your food production has a bacteria in it, that a pathogenic bacteria. There's going to be bacteria, but we need to make sure that we know it's the right one. So what we've done is we've taken these block polymers here, this acrylate polystyrene here, that we can make an NHS ester just to do, chemistry, where we can now click on, most people's favorite bioconjugating use is Trans-Cyclooctene. And we can now use this. We've got polar groups here as our surfactant, as one of our surfactant phases. On the organic phase, we're still going to have fluorocarbon surfactants here. Okay, so take that. We do a Diels-Alder tetrazine click reaction to hang on our antibody. We can now use protein A, which binds to the kind of this part of the antibody, not the active site. And you can see that indeed we get fluorescence. This is a fluorescently labeled protein, and we can detect that indeed we can functionalize our droplets. Take these on now, and we can detect listeria. Here, I'm kind of circling here the gluten. So this is without any listeria. You can see we add listeria to this. We start getting agglutination. We add more. There's 100 cells per milliliter. There's 1,000 cells per milliliter. Here's the process. And again, this is using our program. That's what those circles are. This is the program drawing circles for us and giving us this quantitative data. Okay, so we've done some sensors using, this is all looking at transmitted light. We're doing transmission through, it's a line, you got collimated light. When they're agglutinated, they scatter like bandits, right? But it's often easier to work with things that are fluorescent. Okay, fluorescence is a really nice way to do optical sensing. And so for fluorescence, we need dyes that are soluble in hydrocarbon. That's easy, there are lots of those. Not so many dyes that are only soluble that have orthogonal solubility in fluorocarbons. Fortunately, that's something that's actually before we started these complex emulsions, that's something we have been doing for many years. We started way back making different polymers. You can see this is a polymer that's only soluble in the fluorocarbon. This PPB is only soluble in the hydrocarbon. We do all of our syntheses in these kind of same, we use the same trick we used to make these. We heat things up to get a single phase to our syntheses. Here's a case where we made an N-type material. Again, you can see this is chloroform on top, perfluorohydrocarbon on the bottom. You see this is only soluble in that. And we went on further. Ellen Sletton, when she was in my group, she's now assistant, associate professor at UCLA. She made all these fluorophores. And this was the title of her paper, which we thought was kind of cute. And she's made a whole bunch of these, and she's continued to make all sorts of innovations in this area. But we have a number of these dyes. But we still needed some different ones. We needed things that had a little bit better photophysical characteristics. And so we've also went and come up with some different ways to make. This is like one of my only synthetic slides. You'll see we make a lot of molecules. But this is a case where we do, 8-fold Heck reaction with this perfluoroalkene. Okay, it isn't a great yield, but when you consider it's 8 of them, that's not a bad yield. So this is more than 90% per Heck reaction. And this has, if you look at the fluorocarbon component, particularly the perfluoroalkane, this has 56%, and this is more scattering than anything here that you're seeing. This is partitioning with methylene chloride that you can see that it favors the fluorocarbon phase. Okay, so we have that. We also had some very nice soluble other dyes that do not fluoresce. This is something called a subphthalocyanine. Phthalocyanines look more like porphyrins. This is one that you use a boron template. You can make these subphthalocyanines. And with this terp butyl phenyl on there, you find that these are nice and soluble in basically all hydrocarbons. Phthalocyanines don't tend to be very soluble. So this was something we had to make ones that are very soluble. So why are we making this? Well, it turns out if you pair these two together, what you'll see is that if you're looking from the top, this cyanine, if it's in the organic phase, it'll block light that's going to get to our other dye, prevent light from getting to it. And then also, even if this emits light here, it will reabsorb the light. So this is basically what we call the inner filter effect. So what we were using this organic phase essentially is a filter to prevent light from getting to this bottom one. And so when you look at these, you just see a little tinge of red. This is very, very emissive red compound. And what you can see here is when we add that subphthalocyanine, we just take equivalent, droplets. You can see that we lower the fluorescence from up here to being very, very low. Okay, so how do we now make use of this? Well, we're going to use the same agglutination assay that I showed you before. Where we put our antibodies. We're going to put the antibodies only on the hydrocarbon interface. When the bacteria comes, it binds, it tilts them, and now you see some of the red droplets. They get exposed when you tilt them on their side. The fact is, here they are, exposed. This is again polydispersed droplets. I would like everybody to always make monodispersed droplets, but the research group say, I can turn it. It all works the same. It's just so much easier to make polydispersed ones. But again, here's that same difference here. And what we do is we just take a fiber optic over the top. We're exciting. It's a bifurcated fiber optic, so it excites and it collects light. And we just collect light. And in fact, when we now have our listeria, you can see the light goes up because you're tilting them. You're getting photons in, you're getting photons out. And now you can see that we can get these signals here down again to around 100 colony forming units per milliliter as a detection limit. Okay, so we've used the same thing both in just transmitted light, where we're looking at scattering. We've also used fluorescence. Now, I started out kind of talking about the dynamic aspect of this too. And so can we now use changes in morphology? So right now, I've shown with our sensing, we're using a perfect Janus and we're just changing its orientation. But what about changing morphology? Basically changing the surfactants here that are balancing these interfacial tensions which control this droplet. So here's just a side-on microscope image of a droplet changing shape. And indeed, if we do the same thing, again, now this is again scattered or transmitted light. If we start with the perfect Janus here, we have it here. You can see the happy face that you can see through it. And we basically then add something that basically favors the fluorocarbon phase and causes a change in morphology to where the fluorocarbon phase is on the outside. This is upside down. I should change that. But what you can see here is now we'll get a highly scattering state. You can't see the smiley face. So we just do something like this. We put it inside of an oven. We actually do these at physiological temperatures because what we want to do is just come up with simple bioassay. So here's one for an enzyme called alpha amylase. So what we do is we make droplets. Here now this droplet it has the fluorocarbon on the outside, the hydrocarbons on the inside, shown in red, okay? And it's in that state, okay? Now, if we now take it and we add a hydrocarbon surfactant, we can change it. It'll go all the way to where the hydrocarbon now starts engulfing the fluorocarbon. Somewhere in between there's going to be that perfect Janus, right? Remember that was the same first thing. It's going to have on that coordinate, there'll be the perfect Janus somewhere in the middle, okay? So how are we going to make an assay out of this? Well, what we did is we basically took Triton here, X100, a very well-known surfactant, got this big kind of nonpolar part, and you basically make a cyclodextrin complex of this. Nice water soluble. This sits inside the hydrophobic cavity. But alpha amylase basically cleaves this anomeric oxygen carbon bond here and disassembles it and releases it. It releases it. This finds its way to the droplets. They change morphology. Okay, so we actually now have a way to detect amylase. Okay, we can start out with something that's not very transmissive. Again, it's scattering. As the amylase releases our surfactant, it's going to go up where the hydrocarbon starts gaining. We'll get to the perfect Janus, which is the maximum transmission, and then it's going to go over the hill. Okay. Now, it turns out this is what the real data looks like. So it turns out if we take the time between the maximum point and the half point up the hill, up this, we take that time difference here, and we plot that, inverse of that versus our amylase, our active amylase, we get a nice linear plot. So we can use just essentially these time points here, this from half to full height here on all of these to basically get at quantifying the concentration of active amylase. Now, we didn't patent this. This would be a crazy way to measure enzyme activity. There's much better ways to just cleave things, right? So you all know. But it's a cool kind of concept. And we can do this actually with a smartphone and a light. Just put your smartphone just in the light meter mode. Okay, so again, this is all transmitted light. So just like I did before, like, can we do something similar now with fluorescence? And this is where it got complicated. So we started making different fluorescent droplets and changing their things, and we saw stuff that we had no idea what was going on. And so I called up my friend Matthias Kolla, who had worked on, the transmission optics through these, and his student Cyril Nagberg, who was working with him, and asked us if they could help us. And so what they've done here, what you're showing here, these are the different droplets and the little kind of halos here. That's light coming out. So what they do for each one of these, they do 20 million ray tracing things computationally. That is, you look at light coming out of this, it might diffract out the other way, it might bing bang around this interface. These things, actually, one of our interests in these is lasing cavities. You get whispering gallery modes for light going around. So the light's going around, it's getting confined, it's out coupling, it's coming every different way. This is what they look like. But here what they did is they actually calculated these as a function of the observation angle for all the different morphologies here. And so what we're interested in is looking, remember gravity alignment? We're interested in looking straight up and down at it. We're interested in looking right in here. And you can see there's a fair little distribution of intensity right there as a function of droplet morphology. And so when you plot this out, we get something we call the light curve. Lucas, like I call it Lucas curve, but we called it light curve in the paper. I told him we couldn't call it the Lucas curve in the paper, but called the light curve. He was the person who really found this first. And what we do is we just take this simple little thing. We take our same bifurcated fiber optic. In this case, we put that fluorescent dye in the droplets. So we're getting fluorescence coming out. Okay, we're not doing transmission. This is essentially fluorescence experiment. And you can see here the calculated and observed essentially emission coming out normal. And there is great agreement. In fact, initially this wasn't agreeing perfectly, and it's because we hadn't got the solution right. A little bit of the hydrocarbon dissolves in the fluorocarbon. So to make the perfect Janus, we just needed to tweak our formulation slightly. And Sarah told us that we were messing up and that was what it was. And in fact, when we took that into account, it worked perfectly. Okay, so how do you start making a sensor with something like this? We need to have some way of reversibly or dynamically controlling the interfacial tensions, right? And so one of the things that we've been interested in, again, we like carbohydrates. It's kind of easy things for us to think about from molecular recognition. And you're all probably familiar with the fact that boronic acids bind to vicinal diols reversibly. This is beautiful molecular recognition, okay? It's a dynamic covalent process here. And so we can take and make this boron surfactant. We add a carbohydrate to it. This is, it's a boronic acid. It has surfactant character, but if you stick a carbohydrate on it, it's a much better surfactant because we have all these other hydroxyls on there. And so when you do that, you have the boronic acid as your surfactant. If we add a carbohydrate, it changes morphology. We can change this. Okay, that's good. We actually showed we could detect carbohydrates this way. But we want to, again, detect pathogens, food pathogens. So how might we go about doing that? Well, it turns out that if we use the carbohydrates that are also naturally attracted to salmonella, something like mannam, it's a polymeric mannose, or just mannose itself. What will happen here is we bind the mannose to, the mannam to this, or the carbohydrate. We change the morphology, but then the salmonella comes along and it starts interacting with them. And we got this reversible covalent chemistry. It basically can pull them off. So these are kind of like the burrs that get stuck to your socks out in the woods. You're walking through, they're sticking your socks, you're getting stuck. These things are the burrs that are getting stuck around the salmonella. Now we can do the same thing with the antibody. Antibodies are glycosylated down on their stems. So they bind to the boron. People often oxidize those as ways to bioconjugate them, but we're just using the native, unadulterated antibodies here. They tend to bind to our surface here, probably multi-point attachment. They form robust linkages. Again, salmonella comes in, it kind of strips them away, and we get a change. So now what we do here is we work our way around on this light curve, okay? We initially, prepare them down here where we have, increased our interfacial, decreased our interfacial tension with the hydrocarbon, so we get this morphology. And then when the salmonella comes along and pulls those surfactants off, it pops back. And, crazy way to make a sensor, it really works. Again, we get down to, we're still hitting that same kind of, that same sort of kind of threshold around a couple hundred, this one maybe not quite as good. But again, this was done with live salmonella. We did this on chicken extract. These are data that were done at the USDA under their supervision, where we were taking, and that was one thing I originally thought, how is this, if you use chicken, it's kind of slimy, it's got to have surfactants in it. The fluorocarbons, I think, are savior in all this, because we have so much fluorocarbon around here. So it turns out that this worked really on just, just filter the big chunks out, and chicken extract that's been spiked with salmonella works really nicely. Works both with the antibodies and with mannam here. That's that polymeric mannose. Okay, can you do the same thing chemically? Whoops. So I thought, what would be nice to just run reactions that create surfactants. Okay, and so the thought was, you want to make a surfactant, let's oxidize something, right? Let's just use hydrogen peroxide. So let's make a hydrogen peroxide sensor, okay? Can we take that? And hydrogen peroxide is kind of also good because you can use hydrogen peroxide and couple it to different enzymatic processes, right? So whether it's, glucose oxidase, for example, or pyruvate oxidase, you make hydrogen peroxide. So the thought was, can we make a trigger here where we just take something, kind of a pretty nonpolar molecule, just this sulfide, this methyl sulfide here, and now can we oxidize it under conditions? We had to throw a catalyst in here. We had to throw in Hermann's reagent here, a metal oxide catalyst, to get this to work. But you can make this, and can we now, use this to create a very sensitive sensor for hydrogen peroxide? Because remember, we're not doing a bulk thing. We only have to change a monolayer to change the entire optics of the system, okay? So the idea was, can we use our L curve here to basically do this? And so Daryl Fong did this work, and Daryl initially had a little bit of work to convince me, and he turned out, he came up with a model, and I did not appreciate how basic a sulfoxide was in water. I didn't think sulfoxides, I didn't think of DMSO being a strong Bronsted base, right, as protein in water. But in fact, it does. And so what he finds, that if you just look at the change in morphology, the system is most sensitive when he had a co-surfactant here at the water organic interface of this SDS, the sodium dodecyl sulfate. And in fact, so the reason that this helps is when this is present and he makes our sulfoxide, you get an ion pairing effect. And so you get a surfactant complex that is much more powerful than either one would be on their own. And the important thing about this, I guess it's kind of up here, but we get to femtomolar detection limits with this. Okay, we can get down to femtomolar detection limits of hydrogen peroxide. Lost in my zoom heading at the top there. Okay, so works really pretty well. So you can do this with chemical things. We like converting catalysis into sensing. That's one of the big themes in the group. Okay, so I've talked about transmitted light. I've talked about fluorescent light. What about reflected light? Okay. What about things that reflect light? And so what I'm showing here is kind of pretty picture here. These are, again, droplets. And these little spirals in them are because what we did is we put a chiral pneumatic liquid crystal in it. So it's a pneumatic liquid crystal, is a liquid crystal that all the molecules tend to go the same direction. They're sliding past each other. They only have directional order. They do not have positional order. Okay. And so, and then what the chiral pneumatic does is, in addition to that, locally they'll have that order, but long range they tend to form a helix because I put a chiral element in them. And so that's why you're seeing these little things wound up. These are essentially what we call the pitch. Every time you see this little thing, that's the distance of the helix between those. So the first thing, if you start making liquid crystal droplets, we had to figure out how to organize them in these complex morphologies. And I'm only going to show you one of the surfactants here. We actually have a whole series of these different surfactants to kind of tailor the fluorocarbon interface as well as the hydrocarbon interface. But what we did is a lot of liquid crystals, in fact, is the liquid crystal is something called 5CB. That's a C5 hydrocarbon, a cyanobiphenyl with a nitrile on the end of it. It's a very famous liquid crystal. So it kind of looks like this. Now, this is hydrophobic in the middle, hydrophilic on the outside. It tends to sit like kind of in a little horseshoe thing at these interfaces. And if you put enough of it in there, it tends to align the liquid crystals essentially normal or parallel to that interface. We have another anchor in there that's helping them to align this direction here at the bottom. Okay, we can control all these different things. You can also do with this a simple alkane, just a simple like SDS, you'll get this type of morphology. And if you throw a whole bunch of this and we also anchor it planar here, we get these bipolar things. So this has a monopole at the top, which is kind of cool. And we can get these bipolar ones. And these bipolar ones are really kind of neat because they're kind of lost. They're really aimless. I thought there's a movie supposed to be running here. They're kind of aimless. It's kind of like a slip and slide here. There's no strong anchoring of liquid crystal. And this is what they look like. You cannot stop these. There's just enough thermal fluctuations from looking at things in any light, but they just continue to move. So they're really dynamic droplets. Okay, so back to, we figured out how to align them kind of parallel here, normal there. And what we did is we just make a helix in them by throwing in a chiral molecule. You can throw in a little bit of a chiral biphenyl, or you can do other additives. So we can now make these chiral ones. And so now what I'm showing here kind of is a helix coming out. It's just the molecules are kind of slowly tilting. Locally, they look like they're completely aligned, but over long distances, they are helicizing. And you're probably familiar with these. These are these kind of things you can touch and they change color in their thermal sensors, right? You've seen things like that where they tend to do that. So we can look at it here with just a transmitted light here with no polarizers. You can see those same sort of kind of spiral images. Here's the side-on microscope image. You can again see how the helices are located out. They really look like I have here. And then what now we're doing is reflected light, with and without cross polarizers. This is without cross polarizers, and this is with cross polarizers. Okay, this one should be look kind of odd to you, right? it's pretty cool. So what's happening here, all these little lines when they're coming out, is the light's coming in, it's getting reflected, and it's bing banging over to its neighbor and then coming out. So if you look at any of these lines, they're all connected. In fact, if I had a less regular array, you can have these things over big distances and you'll see all of them connect. They all connect. And so they're all talking to each other and then kicking the light back out again. So it's something kind of very, very interesting and very fascinating about how these things work. So again, we had to play a lot of games. I'm not showing you all the surfactant chemistry we went into. We synthesize all sorts of surfactants. I'm going to tell you, about polymeric surfactants in particular. Okay, so how do you make a sensor out of something like this? Well, the cool thing, Alberto came up with a really cool idea. What he did is he made this polymer here, the block polymer, where he had boronic acid. Remember, boronic acids are nice things to bind to antibodies. We already did that. But in this case, what he did on the other side, in addition to putting something that likes liquid crystals, this looks like a liquid crystal, the cyano biphenyl here, looks exactly like a liquid crystal. He put this binaphol in there. Binaphols have what we call a high helical twisting power. You put a little bit of them in, and they tend to make the molecules next to them want to twist a little bit. They get that strain, you create a helix. So ordinarily here, if those molecules are around and be kind of free ranging here, they all get sequestered into the droplet and they make it twist. They make it chiral. When we react it, we slowly react the outside with our antibody here. We localize them all to the surface. And then the chiral stuff is diminished. There isn't as much chiral stuff on the inside of the droplet, and it gets, the helical twist gets lower. I mean, it's less twisting, it's a bigger period, the periodicity. So the periodicity is determining the wavelength that is reflected at you. And so again, if we try the same things, we can make these things where they have a bigger period. And if we do the same sort of kind of burrs on our socks again, where we take the salmonella and have it rip off all these antibodies and release these things back into the bulk, release this polymer to go back into the bulk, we see a change in helicity. So this is what it looks like just as a function of different cell counts of salmonella. Again, as we add salmonella, we get a change, and we can see different colors come out as a function of salmonella. Okay, so polymeric surfactants are really something that we're really interested in. And here I'm showing kind of the simplest one. This is just like a macromolecular normal surfactant, polar part, non-polar part. But remember, we have 3 phases, right? We have 3 phases. And so we thought, I've been kind of really interested in, like, what if we now start making surfactants that are triphilic? One likes a fluorocarbon phase, one likes a hydrocarbon phase, one likes water. Okay? Okay, so what we have here is these are made by ring open metathesis polymerization. These coumarins here, that's just a dye so we can see where things are. Okay, just throw a little bit of that in there. That's a minority component. But what we have here, we have the hydrocarbon in the middle. That's the one, the H. Excuse just a minute. The water one in the middle. That's the W here, the PEG units. This has the hydrocarbon in the middle. This one has the fluorocarbon in the middle. Okay, so we have 3 of these. And the question was, how effective are these at stabilizing our emulsions? Okay, so one of the things we do a number of different kind of measurements. We do something called a hanging droplet method. It's where you hang a droplet and you look at changes in the shape and use a computational method to determine how much you're changing the interfacial tension. And so what you find is the one that changes the most here is the one that's a fluorocarbon in the middle. Okay, that's the best overall surfactant at stabilizing the hydrocarbon phase. So it's kind of like it has the fluorocarbon in the middle, but it's stabilizing a hydrocarbon droplet. Okay, now, so what we think is going on here is the fluorocarbons tend to aggregate. And so this really looks kind of like the simple surfactant. It looks like it has the water soluble part and the organic soluble part. It's got a little kind of jumble up where it's kind of trying to basically hide all the fluorocarbon, and it tends to interact with this surface. Now, it turns out I've been really interested in how do we get things to only go here at the three-phase junction. There's a line here where there is a junction between water, fluorocarbon, and hydrocarbon, all in the same place. I wanted to get things to go there. And it turns out the way you get things go there is to put the water one in the middle. So this is the best surfactant, but this is the one that goes really selectively to that line there. And we can determine that just by doing fluorescence imaging. That's why we got these coumarins in here. This is some confocal microscope images of it, showing that, indeed it goes to that interface. And so we know that it goes to the interface. And so now what we want to do is we can position it there. Why don't we do some chemistry with it? So what we did is we added another component here. So these are, complicated polymers. They're triblocks, got a fluorescent one. And now what we add is this pentafluorophenyl ester. This is a lot like an NHS ester. It's just better behaved in water solution. It doesn't tend to hydrolyze as fast. So we can take this activated ester. You can buy nanoparticles that have a amine on them. And what we can do is we can react them. So we have them localized around this meridian here, right around that three-phase junction. We throw a bunch of gold particles there, and then you can make some more gold particles around them. And the interesting thing is when you do that, they start, and you look at them, they're reflecting light at you. And the light is, and so unlike most often, the light has a directional component. This one, it has no directional component. It's the same color light no matter which direction you look at it. And that was kind of neat. And we found that, in fact, the color of the light can change with the morphology of the droplets. If we just, in this case, we're just adding some zonals. So we have these kind of gold rings, these essentially particles of gold saturated. They're all localized right around this gap here. And we can change it. And fortunately, between with some help from Matthias Kola and my postdoc, Harry, right there, who goes by Harry rather than his last name usually, but we're able to model this. And in fact, what's happening here is that the light is coming in. These gold particles are acting like these kind of scattering units. They scatter the light and you get total internal reflection, just like the whispering gallery. If any of you have been to cathedrals and things that have whispering galleries, the light comes through, it gets bing bang around here, and then it comes out. And the fact that it's the same, that it's independent of direction, is because of these scattering centers. Because ordinarily it would come out at a given direction, a given wavelength of light. This one basically gets it to where it's directionless by having these scattering features. Okay, one more short story and then I'll quit. Another one on reflectivity. Again, makes use of ROMP polymers. And so these are polymers that originally were synthesized in the group of Bob Grubbs, my PhD advisor, who I miss horribly. He was a great man. Any of you who got a chance to know him, Al worked for him also, know how special he was. Bob had made these polymers, and they got these big groups on the side. So they're you might not call them bottle brush polymers, you call them dendronized. So because these groups are big enough, what happens is the polymers tend to be, stiffer. They tend to be more chain persistent. They don't tend to coil up on themselves quite as much. And they made use of that because they would organize in these lamellae, and they gave nice reflectivity. So we were thinking, like, let's put some reflective polymers into our droplets. And we initially thought, oh, we could do this. We'll make these round things. But what we didn't take into account, unfortunately work for us, is the fact is these things are stiff enough that they don't want to bend these layers. These layers do not want to bend that way. They want to stay, they want to minimize the bending because of this denorization. They want to kind of stay flat. They don't want to have curvature at these interfaces. They're resistant to that. So what we get at the end is we do not get round things anymore. We get essentially the tension between all these interfaces within the block copolymer, which is in a lamellae structure, gives us these elliptical particles. Now, There were some tricks in getting these things to behave. We had to develop surfactants, ones that are more hydrocarbon-like and ones that have more aromatic character to basically stabilize each of these different interfaces. And there's not a huge difference in here, but what I'll show you is there's enough of a difference between just a hydrocarbon and benzene that start organizing things at these interfaces. Now, you can make these different molecular weights. ROMP is like magic. It's one of the most amazing polymerization methods you can imagine. You can make all sorts of different molecular weights, make them different colors. They're very uniform particles here. And here's just some of the color differences. This is what they look like in solution with different molecular weights. But what was most interesting we came up with is look at that. Well, okay, having a bunch of elliptical particles that make different colored solutions, fun, you know, not so unique. But what if we now could take essentially an iron nanoparticle, a super paramagnetic iron nanoparticle. It has an alkyl group on it. Could it functionalize selectively these kind of red blocks? And if it did so, we get little bands of magnetic things. And if you apply a field on that, these super paramagnetic particles will start to interact and form a collective magnetic moment. And that magnetic moment will be directional because it's only these little bands. It's not continuous over the whole polymer. It's important we had these little bands. And in fact is when you do that, now you can apply magnetic fields and you can align these. And so if you just take a solution of these, you know, these are ones that weren't red solution, and you can't see it. There's a magnet over here. Graduate student's taking the magnet. He just turns it one way. It turns yellow. Turns it, and you can see this is even out of the field of view. So this is pretty sensitive. It's kind of cool to be able to take a magnetic field and change it multiple centimeters away, change the color of a solution. Now we've taken this one step further with other types of materials. These are some that are, these are what we call our ice cream cones. There's a little bit of a trick or two in this. We haven't published it yet, but I think you can see here again, there's a solution of them. They're changing color. You can see that we now have a lot more control. And when these things come out, in fact, they tend to be very bright. And there's some optical tricks with regard to these particles that actually give us that bright color that we're making use of. And we have some data. It's not spectacular, but we can use these to detect pathogenic bacteria. It's like what seems like what we do with everything. So anyway, so it's time for me to kind of wrap up. Hopefully I've kind of given you a kind of a tour of like what you can do, just thinking about surfactants and liquids and biomolecular recognition and dynamic covalent chemistry and all these different things. But I think there's a lot to be done here. I think, chemists, it turns out colloid science or emulsions, that's been what mainly engineers have been working on for years, and people in food sciences. Chemists, we haven't been working in that much. I think there's a lot there to be done. So for the students out there thinking about areas to go, there's some fun things to do here. I think these multi-block polymers, I mean, we're just scratching the surface. We just made the first tri-block and showed that we could align things. There are many other things you can do with that. But as all professors say, I didn't do anything. All I did was come up with some ideas, coach people, and raise some money. Very happy for the money, but these are the real stars. I had a number of their names below it. This is a recent group picture in front of the Boston State House. We get dressed up once a year and go out to a fancy dinner. We did do one last September. We did miss a year. The group doesn't seem to like it. They like also the open bar that we have before the dinner. But anyway, I have a great group of students. They're brilliant and very hardworking. And for that, I'm very grateful. So again, thank you, Al, for nominating me or facilitating this lectureship. And I welcome any questions you might have. Thank you.